Hello, welcome to part four of this review of the space program. This part four is going to move to look at several aspects of the space program in terms of contribution to aeronautics, scientific contribution and other programs, the need for cooperation, a brief look at the future. Um, it's not going to be broken down very specifically, in part because a lot of this nowadays is a mix of things that you can imagine happens, in particular in the International Space Station, the ISS. Just very briefly, the contribution of any space program to aeronautics is actually something we don't pay attention to, but it's very strong. It's there. NASA, in particular, itself was the result of the formation of the Army Ballistic Missile Agency, but also the National Advisory Committee on Aeronautics, NACA. And to this day, NASA continues to study new forms of aeronautics to assist, in fact, the aerospace industry. We'll give you a couple of examples, more recent ones. So you're seated on a modern jet nowadays. If you look at the end of the wings, you'll see these sort of little winglets that shoot up. Originally, this was the result of a study that NASA carried out in the 1970s aboard a DC-10, big wide-body commercial jet. And very quickly it realized, based on those results, that you could reduce drag, and therefore you might save gasoline, might save fuel. And so the reduction nowadays, it's pretty common to see pretty much any plane, modern plane, having these little winglets. But the principle of reducing 5 to 6% in terms of fuel consumption, this is not something that people thought about at the time, but very quickly by the 1990s, it became sort of a standard. In fact, you can now retrofit older aircraft with special winglets. That's, in fact, one thing that was studied originally by NASA. Okay, there are many other things, but we don't have the time to look into the detail here. There's because NASA, by the way, is of course a public governmental agency. It is required to, in fact, share the results of its findings. Okay, that's the whole point of it being a civilian agency. Of course, some things are going to remain confidential. However, much of it is published. And because it has a historical function to record the progress in aeronautics, if you go to its website, you will see that there is a remarkable array of documentation available for the public to study: historical, scientific, technical. As far as scientific contributions and other programs go, let's talk about this sort of, a little bit combined. I'm going to talk a little bit about the Europeans first. The third space power after United States and the Soviet Union, or I should say Soviet Union and United States chronologically, was in fact France. In 1965, France orbited its first satellite, A1, nicknamed Asterix, after the comic book character. It's pretty common to have sort of popular culture in place to also sort of, help people adjust and appreciate the concept of space. One of the very first lunar modules, for example, was named Snoopy, and the command module was Charlie Brown. So anyway, Asterix was orbited in 1965. It was grounds for, of course, great celebration, showing that France could also do its own sort of, technical developments. But the complexity and the cost of it was, of course, remarkable. This was very much a political decision initially. The French CNES, which is essentially a counterpart to NASA, was more of General de Gaulle's brainchild, a way of, showing autonomy vis-a-vis the Americans and the Soviets. Eventually, it will be far less political and far more scientific and technical. But initially, it was a way to sort of show off. It was a prestige instrument, one has to say that. That said, the technical achievement was remarkable, and it allowed France to sort of give an impulse to what you might call Space Europe. Space Europe, however, is very expensive, and so very quickly France realizes that you can't just have a budget that would be on the size of Apollo's budget, $24 billion by the time Neil Armstrong stepped on the moon. In fact, you needed to have the cooperation of other agencies. Excuse me. One will be the European Space Research Organization, which will be essentially an assemblage, a committee of multiple countries involved in orbiting scientific satellites, and in particular TV communication satellites manufactured by Germany but orbited by NASA. In other words, ESRO will pay NASA to send satellites, European-built satellites up. ESRO is, in fact, a pretty successful element of early space Europe. Later on, it's going to form the basis of what will be the European Space Agency that we still know today, ESA. Less successful will be ELDO, European Launch Development Organization. ELDO, in many ways, showed how amazing the integration in the construction of the Saturn V, and of course its successful operation was. Saturn V was the reflection of sort of a masterful integration process with NASA essentially controlling all the levels, but farming it out to different companies. The Europeans tried to do that. Okay, you have to be fair to them. Except that, of course, you've got, basically trying to do something for off-the-shelf materials. So one stage was going to be built by the French. Another stage was the British stage because the British had their own blue steel missile that they were planning on using for their nuclear program. And then the blue steel had been canceled, and so basically it was a way of giving British aerospace industry something else to do in terms of rocketry. A third stage was going to be, well, for good measure, German. In other words, and of course, the whole thing was going to be fired from where? Well, initially it was going to be out of Australia, Woomera in particular. And this rocket, civilian rocket, composed of multiple countries' contributions. The idea was there. The idea should not be shot down, but the rocket itself was nowhere near ready. And so as they tried to fire this rocket several times, it failed on each occasion. So Europa was a fiasco, but you could argue it's a successful failure. This successful failure will in fact become the ancestor of the European Space Agency, as well as the Ariane family of rockets. So how do you create a European Space Agency? The space technology, the international cooperation is all done for shared benefits. And you need, especially in a Europe that is composed of 27 autonomous nations, to have this process of maybe getting back what you put in, okay, and also having a very clear goal that you can sell not just to budget-minded governments, but also to the public. And so, how accurate is this promise of employment generation? Well, it is in terms of scientific contributions. Poverty alleviation, maybe. Higher literacy, definitely. Perennial clean energy, that's wishful, but they are working on it. Improved quality of life, again, at what point will that be like poverty alleviation? Will that really help? Wealth and welfare of society, wealth, definitely. Okay, this is in fact a very costly program. Welfare to society. Is there a trickle-down element? For some companies, there is. Therefore, there is more employment. You can make a case or you can fight the case, but this is essentially the rationale. You couldn't simply just say, we're going to do it because the Soviets and the Americans are doing it. You needed to have a rationale behind it. And so the European Space Agency was formed in the 1970s, and as it developed rockets, I'll talk about that in a moment, it also developed means to collaborate in space, in particular with NASA. NASA was looking for partners when it can design the shuttle, especially to carry and sell essentially space on board its space shuttle. And the Europeans came up with Space Lab, which was a fairly successful thing, but wasn't orbited very often. The idea was simply to have a space station that would go into orbit. You can see it here in the back of the shuttle, and then be used for the 10 days to 2 weeks of the shuttle mission, and then come back with its experiments. This will be, for example, the site in particular of the first German astronaut on board. And it is a success in the sense that it gave the European Space Agency ideas for the design of its portion of the International Space Station. But otherwise, it was limited in its use, partly because there were a limited number of space shuttle missions available to sell to the European Space Agency. In parallel, the European Space Agency oversaw initially the management of the Ariane rocket system. Arianespace is now a semi-private corporation, um, uh, partly controlled by the French government, but also cooperating with the Russian government, the Russian Space Agency. And so you've got a whole series of Ariane family of rockets. Ariane 1 was first took off on December 24th, 1979. They had some problems as they developed it. Okay, Ariane 1, the prototype worked, but the second one didn't do so well. One of the big successes for many years was Ariane 4. That was perhaps the most mature and most successful of the Arianes. It has since been retired, and after some initial difficulty, the Ariane 5 was put together. By the way, this is not to scale. Ariane 5 is substantially bigger. Okay. Um, Ariane 5 it was essential to keep Europe competitive because you could orbit, in fact, not just one but multiple satellites, depending on how many you squeezed in under the cover. Okay, this is again the result of this time successful integration of the technology. In other words, you have contributions from Germany, from all the various nations involved, and time and again you see the multiple flags. Okay, from Europe that are involved in the construction of it. The Swiss, for example, make the cover, and so on and so forth. So all these things suggest that Ariane 5 is basically sort of the success story for the European Space Agency. Ariane 6 is now under consideration, but it may take several more years depending on how successful the market is or not, because this is a money-making operation to recoup investment, but also to justify some of the huge budgets that are expected to maintain, for example, the launch facilities and the whole bureaucracy around the European Space Agency. In that regard, let me talk briefly about the European mini shuttle. The European mini shuttle, Hermes, was initially a French idea, okay, where, of course, the Europeans were going to participate, especially in terms of the money. The French were designing it. It was going to be built in probably by Dassault, the French aircraft manufacturer. And eventually, by the early 1990s, it was very clear that this thing was extremely costly, that the technology was very complex, far more complex than anybody had imagined. And again, the question was, what are you going to use it for? You would have had two astronauts in there, and then not even really enough space for much more than maybe a small satellite. So was that going to be kind of a rescue pod? Then why not just have a little capsule? Wouldn't that make more sense? In other words, very quickly, the mission became unclear in regards to the Hermes spacecraft. And so eventually Germany was the first to pull the plug financially. And so very quickly the project was abandoned. The full-scale model of Hermes was donated to the Musée de l'Air in Paris. I'm not sure it's available to be seen. It was in pretty bad shape in any case. But this was essentially sort of the end of this mini shuttle European adventure. In fact, this mini shuttle was going to do things that the space shuttle itself, the US space shuttle, was already doing. So why duplicate the effort? On the other hand, more successful was the development of a servicing module for the European Space Agency, in particular the ATV, Jules Verne. And there was a series of others that were orbited atop an Ariane 5. This essentially showed that at least going into working in terms of unmanned modules, you could in fact do it. And manned modules were going to be left to the Russians and eventually to the Americans, who are working on a replacement for the space shuttle. What does that all mean? Let's be a little bit cynical here, or ask the difficult question here. Is that really useful to have a European Space Council and then the EU Council itself? How much of a bureaucracy is it? What a problem that is. The reality is that you have to view this as one of the outcomes of the Franco-German couple, which in the 1940s and 50s realizes we need to stop beating the crap out of each other, to be honest. France and Germany had gone through 3 wars in 70 years, including 2 world wars. And very quickly, what you would call essentially the fathers of European unity, however limited it may be, Maurice Schumann, General de Gaulle, Konrad Adenauer, the first German chancellor after World War II, all realized that you needed, in fact, to start having cooperation. And cooperation had to be done also in the form of education. Student exchanges, starting in the 50s and 60s already. And these student exchanges were essential. True, that ironically, these are the very students who, for example, caused 1968, okay, but also who started having more of an open-minded approach to things. The perfect example, of course, would be the Airbus conglomerate that many of you know through Toulouse. But this European Council overseeing what the European Space Agency and having a joint task force consulting in terms of what to do in terms of the sciences. This is what helps, in fact, direct Europe. It is slow. It is sometimes difficult to reach a decision, okay? But still, there is, in fact, an essential process of cooperation that you wouldn't have had otherwise. So, starting about 20 years ago, there's been this sort of new chapter in strategic European Union vision. In other words, what are you going to do with space? Okay. What kind of space priorities should Europe have? Do you just go into space for the sake of going to space? Do you fund the International Space Station just because? Or do you mobilize specific resources, scientific skills, but you do this in specific projects? And there was a whole series of projects that the European Space Agency has undertaken. In particular, for example, landing a probe on an asteroid successfully, in fact, or participating in a deep space probe. All these things that we don't necessarily think about because we're very often focused more on the human dimension of space travel. In fact, this is what the European Union has embraced. In addition, there's a whole series of projects about looking at Earth, trying to understand the environment. All these things are undertaken with help of the European Union. Let's talk a little bit about the human dimension again. The in the 1970s and then in the 1980s, first the Soviets and then later the Americans, but the Soviets took to bringing into orbit guest cosmonauts, and they were from various countries that were friendly to the Soviet Union. So the first black person happened to be a Cuban fellow in the 1970s. Later on, there was, for example, an East German person, a Mongolian, etc., etc. Well, in the late 1970s, France fields 2 spationauts. Why call them spationauts as opposed to astronauts or cosmonauts? Well, it was just the time of the Cold War, and so the idea was to also find sort of a term that would be sort of very, very French. The term has sort of disappeared nowadays, but you can still see it occasionally used as a synonym for astronaut or cosmonaut. Astronauts were Americans, cosmonauts were Soviets or Russians, and of course, spationauts were the French. So this was sort of the very sort of point of pride, and splitting the difference. Colonel Chrétien, at the time Colonel, now General, orbited aboard of Soyuz in the early 1980s, and in the mid 1980s, Patrick Baudry joined him, but this time aboard a space shuttle. You've had multiple other French astronauts since then, and of course European astronauts, Swiss, German, British, etc., Italian, Spanish. But perhaps if you're interested and if you're able to read French, I recommend this graphic novel about the story of Thomas Pesquet, who spent several months aboard the International Space Station, and who summarizes a little bit the complexity, but also the in a humorous way, the challenges about going into space. Let's talk about other programs. I've chosen these two caricatures on purpose. When China had its own rocket program in place, which and still is very much under control of the military, and then to the surprise of everyone in the early 2Ks, the Chinese actually put an astronaut in space, but not on board either a space shuttle or a Soyuz rocket, but aboard one of their own rockets. And so this sort of caricature representing the Starship Enterprise, wondering what kind of aliens have just joined them. Well, in fact, here come the Chinese. More on that in a moment. In parallel, when India also initiated its own space program and successfully shot its first rocket into space, in other words, orbited it, the New York Times ran a caricature about the elite space club with a caricatured Indian and his cow, knocking on the door. This was deemed very pejorative, and the New York Times was heavily criticized for running that caricature. In fact, the New York Times doesn't run caricatures, but it had republished a previously edited caricature from another newspaper. 10 years later, essentially, India could claim a record of 104 satellites successfully orbited. Some of them were Indian, some of them had been sold, in other words, to other nations. And in fact, other nations came, knocking on the door, asking the Indians for a space on board. In other words, you now have a whole commercial space program in place, where Arianespace, which used to control about 80 to 90% of the commercial launch market, is now competing with the Chinese, with the Indians, and with the Americans and Russians also. And so this is sort of the response from an Indian cartoonist to this initial caricature that was published in 2007. Briefly talking about the Chinese. So the Chinese program has often been described as a kind of a maze stuck in a labyrinth covered by a secret. We know very little about it. We know that the Chinese have a whole series of rockets, the Long March series, and we know that their very first cosmonaut, sometimes known as the taikonaut, to mark him as separate from a cosmonaut or an astronaut or a spaceonaut, bless you, is successfully went into orbit. You've had also sometimes some Chinese who have actually orbited, used sort of Russian know-how to get into orbit, and this has also been done. Probably the next stop will be about at least orbiting the moon, but we don't exactly know when this will happen. The element of secrecy is so substantial that we're not exactly sure, beyond official communiques, what China is up to. But this is becoming essentially a very strong space power. It has the wherewithal. It is perhaps one of the most staunchly military or militarized programs besides that of Russia. Russian Space Agency was always under control of the military, perhaps less so now, but in the case of China, it is completely under control of the military. This gives you a sense of the type of rockets that, for example, the Indians are working on putting together. And here I'm talking a little bit about a different group. The Chinese are also, of course, putting together their own thing, but the Japanese are also involved in that. And this is the Indian space program. I'm not going to get into the detail here. Each of these would require their own sort of, survey. The ideal was that by 2020, the first Indian indigenous manned space flight would take place. This has not happened, partly for technical reasons, independent of the current health crisis. It may take place later on, but we're not exactly sure when. There is also the idea of a mission to the moon. The mission to the moon was not entirely successful. In other words, we think that the probe crashed when it tried to land. But still, the fact that India is trying to get to the moon with an unmanned probe also suggests that basically we are now in the second or third generation of space, with new powers trying to repeat and also not just emulate, but also improve on the efforts of the Americans and the Russians in the 1960s and 1970s. The orbital vehicles themselves, for example, in the case of India and China, some of them are heavily inspired from the sorry, the Russian space program, but now they're in fact very much their own indigenous design. What are other countries up to? Well, you've got the British National Space Centre. It's at the heart of the United Kingdom's effort in space. The UK is notoriously limited in its contributions to a space program. It has, in fact, coordinated civil space activity. It has participated on occasion in various European programs. But overall, this has not been, contrary to, for example, the ideals of the British Interplanetary Society of the 1930s or the 1950s, has not been sort of, at the forefront of much investment in a space program. It does, however, support academic research and tries to nurture the UK space industry, again, in a support position. Germany, on the other hand, is substantially involved, but with very clear, very precise goals, commensurate with a budget that it controls very precisely. The idea is indeed that Germany would like to participate in the exploration of Earth and the solar system. It wants to also focus on helping with the environment. Germany was one of the first nations as early as the 1970s to become concerned with the environment. And it would like to see more work done with satellites to, for example, identify problems with the environment and ways of protecting the environment. How to do all of this? Well, how about a space station? Remember, we talked about the space shuttle that had, being devised, and the idea was that it was going to go to the space station. Oh, right, there was no space station. Skylab was, of course, not in place. When we think of a space station, we often have perhaps a vision of a space station like that of Stanley Kubrick's from 2001: A Space Odyssey. This sort of self-rotating space station. Therefore, because it rotates, it creates this artificial gravity in its outer ring. These kinds of things, of course, would be extremely expensive and extremely difficult to construct. But this was one of the ideas in the late 1960s, that you would indeed have a space station in Earth orbit for people to visit, but also to carry out scientific experiments. When we think of a space station, of course, we are very often tempted by science fiction. Here, a peculiar meeting between two very different scientific visions, Star Trek versus Star Wars. But of course, whenever you've run out of planets in science fiction, you just add a space station for good measure. What about the real stuff? Well, in 1987, the United States announces the planned construction of the space station Freedom. This is in response to Soviet efforts. The Soviets, in fact, after the failed moon race, had refocused their efforts on building a whole series of orbital space stations. In particular, the Salyut space stations. Most successful ones were Salyut 6 and Salyut 7, and then eventually the Mir space station. The United States, of course, with its beautiful shuttle, it's incredibly complex but also very advanced system, needed to have its own space station. It was not to be. This was going to be way too expensive to manufacture. And with the end of the Cold War, the notion of having a US space station on its own made no sense. It was better to go to the Soviets. Now, the irony is, of course, the Soviets had the space station, and you can see it being serviced by, Soyuz and the Progress cargo ship. And of course, this drawing suggests that there's going to be a Soviet shuttle servicing it. This was not to be. So basically, by the early 1990s, it would make sense to have the US space shuttle go up to the latest Soviet/Russian space station, Mir. Mir was the ultimate achievement of the Soviet space program, and it was a remarkable one, even though towards its later years it suffered from substantial technological issues. It even had a fire on board. But still, the cooperation between the Americans and the Soviets was remarkable. What the United States quickly realized is that you could have space missions that went 10 days to 2 weeks in orbit, but could you really remain in orbit for a long period of time? What would it take for humans to live in space? And this is one of the big questions we have. What does it take? And so the best way to do so was to cooperate with the Russians, who already had placed cosmonauts in orbit for months at a time. In fact, to this day, the record is held by a Russian, uh, almost 400 days in orbit, something like that. So well over a year. Um, this process of cooperation is going to give a remarkable information to all sides involved in order to actually construct the International Space Station. In addition, United States will contribute through other studies. For example, the Long Duration Exposure Facility, LDEF. It was orbited by a space shuttle, and then it was retrieved a few years later. And aboard this LDEF, you had all kinds of various materials that had been placed to study basically their exposure to space and to understand essentially what it would take to build an international space station that would last, several years. So all this scientific achievement and accumulated knowledge is going to help build the ISS, the International Space Station. Um, if you think of the ISS, think of essentially a kind of Lego assemblage. Of course, far more complex and really reflecting truly a masterful integration. I mean, you're talking of not just multiple agencies within a government, but multiple international governments, each contributing their various labs. Okay. Um, and it's going to take, of course, the cargo facility that the shuttle offers to construct the International Space Station, after which the space shuttle will be retired in 2011. And also the rocket capacity that, for example, Russia has with some very heavy lifters. All this will result in this kind of a gigantic dragonfly. This, of course, visit from the shuttle did happen, but only until 2011. Since then, the ISS has been serviced by Soyuz rockets and Progress cargo ships, as well as the ALV of the European Space Agency. Uh, Eventually, there will be a new American system that is supposed to become operational in the early 2020s. For good measure, of course, you need to again have a little bit of sort of levity, quite literally levity and gravity. Speed limit of 17,500 miles per hour. This is, of course, the necessary speed you have to achieve to stay in orbit. What of the European contribution? Well, based on Space Lab, the European Space Agency designed and built Columbus. Um, and it is an intricate part of the intrinsic part, sorry, of the International Space Station. If you think of the International Space Station and all these different sort of countries' labs, you have to think of one of those 19th century apartments where you didn't have a corridor. You basically went through each room to get to another room and so on and so forth. Well, it's a little bit like that. Okay, so say you want to go to the observation area, you're going to, maybe, go and visit on your way the Japanese section or the American section, etc. This European, or not, rather, international presence in space, what does it involve? Well, it's about learning also to live in space, not just together, but also just live in space, period. Think about it. Say you woke up this morning, okay, you had your cup of coffee, you took a shower, of course, you changed your clothes, maybe you did laundry, you went and bought cigarettes if you smoke, or your newspaper, and so on and so forth. None of this, of course, can happen the same way in orbit, okay? Can you do laundry? Not a chance. Okay. Can you take a shower? Nope, that's not how it works. You do essentially sort of wet baths, with no sponge baths. Um, what about your underwear? Okay. Do you use a paper underwear that you would just throw away after a while? All these questions have to be answered. So what we take for granted in everyday life has to be solved in space before we can, in fact, hope to undertake a mission towards Mars. In addition, these scientific experiments on board the International Space Station are essential. It involve anything from crystal growth to questions of cell development. But for some experiments, you might not need to go all the way up into orbit. So you have a whole series of experiments that you would have normally been carried on in space that are being done either aboard what they call zero gravity airplanes, where the plane sort of rises up and then falls for about 30 seconds, thereby giving an element of weightlessness. It's something that is used to train astronauts to the idea of weightlessness, but it's also something that can be used for scientific experiments. There's also the idea of a drop tube with a drop tower that gives you a few seconds of non-gravity as the container falls to the ground in a controlled experiment, of course. And this is done as a way again to study, for example, the reaction of certain processes or chemical reactions without having to go into space. Finally, what is the International Space Station about? It is about having a permanent human presence. It sounds very sort of light, but it is in fact symbolically important. By becoming adjusted to living in space, we can in fact talk rationally about going maybe to Mars, or about establishing some kind of a permanent space station where people could simply live and work in space, but beyond what the specially trained astronauts are doing nowadays. One big problem, however, is that we are also causing difficulties in space in terms of the environment. What you see on the left here is a schematic of one of the first studies done of what happens when, for example, a rocket explodes as it is about to reach orbit. And many of the pieces still go into orbit and remain there. Some of these pieces, are easy to track. Okay, they can be seen on radar. There are anywhere from 5,000 to 10,000 such pieces that can be tracked. What cannot be tracked is smaller pieces, paint, a bolt, stuff that was ejected in an explosion. And so what you can see here in terms of this Ariane explosion, you have to multiply it by all these rockets that we put in space and which don't necessarily leave orbit and burn up in the atmosphere. Have there been any solutions to that issue? Not yet. In fact, anything that is floated about involves substantial costs. Why would you pay so much money to collect trash? Well, perhaps the rationale would be simply the way we, pay money to collect trash at home. But this is not a problem that will go easily, and it will threaten any human presence in orbit. In closing, I want to talk just a little bit about this notion of actually space travel. I mean, we went to the moon in 1969, ended that in 1972. We haven't been back. Is it time to catch our breath? It's possible, but wait, no, how about going to Mars? Many private companies are eager to try out for this. Going to Mars has been done in terms of robots, but could you do it in different ways otherwise? Are there alternatives to rockets? Well, not yet. Okay, so we're not at the Buck Rogers style possibility. And to give you an example, one of the problems is of course finding the necessary fuel, but also achieving the necessary speed. Distances in space are beyond anything we can imagine. So say you're trying to reach the Centauri cluster, star cluster, which is technically the closest one we have outside of our solar system. Well, if you're going, typical 55 miles per hour, you can see how long it's going to take. It's going to be a while. If you were going to go to speed of an Apollo space capsule, taking 3 days to reach the moon or 3 days to come back from the moon, then we'll be in touch in about 900,000 years. If you were able to go much faster with a probe at a substantially even greater speed than the Apollo one, maybe you could reduce that to 80,000 years. What would that probe do once it arrives? Who would be home back on Earth to answer its call 80,000 years later? And so, of course, the logic is what a lot of people have said with regard to science fiction. You need to have the light speed breakthrough. So Star Trek, Star Wars to the rescue, of course. Of course, we have issues with that, as you can imagine, because you have this problem of the absolute speed that you cannot break. In other words, which is the speed of light, 300,000 kilometers per second. Um, so a lot of people say, well, you know what? If you compare it to the history of aviation, we will get through it. Simply look at the way it has worked for the sound barrier. There was conjecture, there was speculation, science identified, the Mach number, technology starting in World War II and just after, discussed the possibility of, high propulsion speed, and then it was applied. And so in 1947, we broke this acoustic or sound barrier, and there was in fact electromagnetic existence that made clear that this sound barrier existed, that you had to find ways to break it. Okay, so why not do so with, okay, fine, maybe the Starship Enterprise, but a light barrier? Could you go through this? After all, in science fiction, this thing does it. Well, you've got electromagnetic barriers and you've got electromagnetic existence again. Okay. Yes, but the speed of sound is not an absolute. Okay. The speed of light is an absolute as per Einstein's theory. And so the theory goes, if you approach the speed of light and in fact go at the speed of light, not even break it, but go at the speed of light, you become light. Oops, energy, which means that essentially you're out of luck. Okay, you will transform into something else. What exactly, we don't know, but presumably you will die. There's another problem with that special theory of relativity that, of course, posited this absolute speed of light that we still rely on in physics. Um, uh, there's this notion of time, and time we think of it, and when we are human, as sort of an absolute. The time, for example, we are spending together in this video. Um, but time is also always relative to the observer. This is not a lesson in physics. You've got some physicists who could do a far better job than I can to explain it. But I remind you of an interesting uh, explanation that was posited in part by Carl Sagan, a great physicist, in the 1970s in a popular show, in which he described two twins. One decided to go for, well, not even so much to go on Earth, but simply go for a motorbike ride, except that motorbike could go to close to the speed of light. So not 300,000, but let's say about 200,000, 250,000 kps. Problem is, when you go close to the speed of light, time slows down. It's one of the aspects of the special theory of relativity. So that twin is on his motorbike going close to the speed of light, and his other twin is sitting on the bench waiting for him. The hour passes, okay, when the twin who went close to the speed of light returns. In fact, he has aged far more slowly, okay? And so for that twin, maybe half an hour has passed or an hour, but for the other twin, several years have passed. And this is something that also would require solving, okay? Could you in fact have, let alone astronauts, but even machines that could deal with that? To achieve, of course, that speed of light, assuming you were able to break the laws of physics, which we cannot, we can simply play with them, but we can't break them, then you would have to, look for a different kind of rocket performance. So we've got chemical, we've got nuclear, we've got ion plasma, the thrust, but of course the quantity of all this needed is a big problem. More on that in a moment. This is where we want to be, okay, in terms of rocket performance. So in other words, we once again are nowhere near finding a proper solution. There's also the question of the propellant mass. And you can see here, this is borrowed from a scientist who put it together in the 1990s. If you wanted to send one canister, so not something very big, okay, a canister with scientific experiments to the Centauri cluster within 900 years, in other words, sufficiently fast, okay, to still have someone at home answering the phone. Sorry, the radio. You can see basically the difficulty of doing so. Chemical process, fission process, fusion, both of course are nuclear, or an ion antimatter. Antimatter is something that is always very attractive to us, especially in science fiction. Problem is, we don't know how much antimatter there is in the universe, and even if there is, how do you contain it? Okay, if it's antimatter. In other words, you don't even need to be a physicist to realize that this process is absolutely sort of very difficult to identify. As far as a chemical reaction process, the theory goes we wouldn't have enough mass in the universe to have enough fuel propellant that way. Fission and fusion, you would, okay, but you would need basically sort of the equivalent of 10, railroad tracks, railroad cars, sorry, of ion antimatter to be able to reach this kind of propulsion just for a small canister. And so in the foreseeable future, we are not going anywhere outside of the solar system. We can send probes, okay, who are going to take years to leave the solar system, as happened with the Voyager probes launched in the 1970s. But otherwise we don't have the physical knowledge the scientific knowledge to do so. And of course, when I say we haven't even talked about the brakes, yes, say you've reached close to the speed of light, how are you going to slow down? You do have to. After all, you do plan to get into orbit wherever you're going, right? So these are all problems that we have, which is why if you look at sort of the wider history of the space program, we may have already reached a plateau. In evolutionary biology, we sometimes speak of saltation. Well, maybe there is that too in space travel. Think of perhaps not an ideal comparison, but one nevertheless worth making. Sail matured pretty much by the 16th, 17th centuries. Okay. And basically, sure, you improved on the size of the boat and the shape of the boat, but overall, the technology of the sail reached a plateau by, the 16th century, so the 1500s, with some improvements here and there. And then basically there was no saltation, no new progress until the invention of the engine. Okay. Diesel engine, gas fuel engine, what have you, in the 19th century. In other words, this is when the saltation happened next, 400 years later. Okay. You could say the same thing about aviation. Okay. Where, for example, if you look at a typical jetliner in particular, or even a jet fighter, okay, we have reached a certain maximum speed. To go beyond this, we could if we wanted, but what would be the point of it? And so we're all stuck either in sub-Mach speeds in airplanes, or planes that go at top speed of Mach 2, Mach 2.5. In fact, more recent fighter jets are not even designed to go Mach 2. What is the point exactly? Okay. So again, we may have reached a plateau in aviation. Well, here in the case of space, we know we can go to the moon. We know humans can live in space, but we don't yet know how long, how well. And so these are all, great problems to have that we need to solve together. But it probably won't be solved until maybe many generations after you and me. I thank you for following this brief little overview of space program. Hope you enjoyed it, and hope to see you on some other episodes of the Aero Masterclass out of Toulouse. Take care. Bye bye.
This video is not ended. Please let your questions or remarks in comments. We will be glad to answer them. Subscribe, like and share to help us making this channel well known. See you soon!